Okay, kids, here we go. We are going to dive into our terminology sheet. We got to learn to talk the talk before you can start walking the walk here in chemistry. So go to your essential documents in your modulus, click on it, download the topics for today, that being Monday the 18th. Okay, you download that, doggone it. You go and you do it now. Oh, wait, you're going to need them, okay? It looks like this. It's got all our topics on there. Go do it. Go get it. Oh, wait. Got coffee today. Okay, thank you. Thank you for coming back. Okay, you got it? Okay, so I'm going to go down and do some of these words, some of them kind of quickly. And here we go. This is some terminology. Now, could you look this stuff up on your own? Of course you can. You're all relatively intelligent people out there. You could do this. You can go look up these definitions. But I'm going to go through them, hopefully explain some of them, and that'll help you maybe memorize them a little bit better, and you'll have them right there at the tip of your fingers. All right. Ooh, got coffee today. I'm so pumped. All right, now. First one, on our list, you can see, says qualitative versus quantitative. The word qualitative, that means without numbers. So a qualitative observation in science would be one using, basically, it's using your senses. So what you see, what you hear, what you smell, what you touch, what you feel. This feels smooth, okay? If I touch something which is like glass, it feels smooth, and that would be a qualitative observation. I see a red banner in the back of the room. Yeah, you can't see them, but I've got my Game of Thrones banners up in the back. House Lannister, okay, nice and red back there. I can see it. I can see it. And so that would be a qualitative observation. Quantitative, on the other hand, has to do with numbers, quantity, numbers. So numbers, meaning I weigh 195 pounds, okay? Yeah, okay, I've been gaining weight for doggone it during this lockdown. I can't get out and get my exercise, all right? And my hair's getting long and out of freaking control. I haven't had a cut in 7 weeks, and I'm gaining weight just by breathing. Sorry, I was venting, I apologize. I feel better though. So yeah, that would be a quantitative measurement, how much something weighs, what the mass of something is. And they're not the same thing. We have to go through that shortly. Mass and weight, not the same thing. So, oh, and maybe, oh, look at there. That person looks like they're about 6 feet tall. Quantitative. Anything that has to do with numbers is quantitative. Volume measurements, length measurements, time measurements, all that international system stuff. Those are all quantitative measurements. And in science, we typically want those. Those are what we're looking at for data. Numbers, data, you need numbers to analyze in order to get good conclusions. You need a lot of data, quantitative measurements. All right, moving on, that's that. Law versus theory, that's next thing on your list. I actually loaded in for you a nice little video that explains it quite well. Watch it, law versus theory. Bottom line is law is something that happens over and over and over again. It's what happens, it dropped, okay? Law says drop. Theory explains why it dropped. So theories try to explain laws, but they're based on laws. Theories are based on laws. You can't have a theory without law to back it up. Laws never change. Theories can change. Theories can, ready for this, evolve. Those are good because evolution's a theory. And things can change. So theories can change. Okay, they're not 100% stuck in forever and ever and ever. They're always going to be true. There could be data that will have to be incorporated. New data shows up. You have to incorporate that data. You adjust your theory a little bit. So laws, always let go of this thing, falls. Law of gravity. Theory of gravity will explain why that happens. Okay, what's going on? What's the theory behind why that would happen? That I would let go of this and it would fall instead of just hover. That'd be kind of cool one day if you take something and you drop it and it just hovers. I would either say aliens, that's what's making it hover, or whales. Whales are aliens. You don't believe me? Check it out. You know, someday you'll find that out, and you heard it right here first. Remember that crazy guy? He said whales are aliens. Yeah, I said that. Okay, moving on. So we have matter. Matter is anything that takes up space and that means has volume and has some mass to it. So something which is matter is going to have mass and takes up space, has a volume to it. So is light, let there be light, is that matter? The answer is no, it doesn't have any mass to it. But I mean, it's kind of weird. I mean, we can get into funky physics. I love it. I love physics. But you know, stick with chemistry here. But you can get into, you know, what is light? And I'm going off on a tangent again, never mind. But light's not matter because it doesn't have any mass. It has mass-like properties, but no mass. Okay, so and you can see on the list I put mass, and I put a little asterisk there. I wanted to go over what mass is. And chemistry books tend to get this wrong. And I don't know why they do this. I don't know. I don't know. They don't listen to me. What do I know? Physics books tend not to get this wrong. But if I were to ask you, what is mass? Many of you would say, it's the amount of matter. The amount of matter in something, that's the mass. And I go, nah, no. But my chemistry book here says so. I know, it's wrong. Well, how come you're smarter than the chemistry book? I don't know. But I can tell you that, and I'll show you logically why that's not true, that mass is not the amount of matter. Mass is a measure of inertia. Mass is a measure of inertia. And everybody knows, you've heard of inertia, okay? Remember inertia? The oldest sister on the Brady Bunch? Inertia, it's always about inertia, 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 inertia. That was Jan, she was always jealous of inertia. Oh, it wasn't? Oh, it was Marcia. I always get them confused, Marcia, inertia. Moving on. Okay, so it's a measure of inertia. Well, what's inertia? Begs the question. We have to know what inertia is if we're going to say this definition of mass is the measure of that. Well, inertia is the tendency. It was my quick definition. It's not going to be textbook perfect, but it is. This is the explanation. Something wants to keep doing what it's doing. If something is sitting still, it wants to keep sitting still. It doesn't want to move. If something is moving, it wants to keep moving, and it doesn't want to stop or slow down. Slow down or speed up. It just wants to keep doing. Things want to keep doing what they're doing. So if I have, you can't see it, but here's a book. If I have this book on the table, and then just sitting there on the table, it wants to sit on the table. It's not going to do anything other than sit on the table unless somebody forces it to do something different. So I can force it to move. Yes. All right, but I didn't want to do that. You heard it complain, right? You can hear it. No, don't do it, don't. See, it's complaining. It didn't want to move. I made it move. I forced it to move. If something is moving, it wants to keep on moving, and it will keep on moving until it runs into something, or it slows down due to friction. Those are forces which cause those changes in motion of something doing what it was wanting to do, which is whatever it was doing. I hope that kind of makes sense. So how is mass a measure of inertia? Okay. If I have a book on the table, and this is a paperback book, it's kind of light. Oh, look at me, lift, lift, lift. Nice and easy. This book here, my chemistry book, is much heavier. This one's heavier. I got to put this down. I can't. I'm telling you, I'm out of shape. I need to get more exercise. The heavier book was, if I want to move the heavier book, it's going to take more force to do it. Why? Because it has more mass. Something which is heavier, let me draw this out here for you. So I've got a book that's paperback, and I have this large book which is not paperback. If we were to take this and mass it, and put it on a balance and mass it, maybe it has a mass of 10 kilograms, and maybe this one has a mass of 2 kilograms. Okay, well, how is this a measure of inertia or resistance to change in motion? 10 kilograms sitting there, 2 kilograms sitting there. I want to push them. Must use force. Let the force be with you. If I want to push this one, and I can only push with, let's say, 50 pounds of force, that's all I can push. That's all I got. I only got to be able to move 50 pounds at most. I'm just, again, out of shape. So if I can move this with my 50 pounds of potential force, and this one then with 50 pounds of force, which one's going to move or accelerate more, faster? Well, this one is. It's lighter. Doesn't have as much mass. This one has more mass. I can't move this one, accelerate it as quickly. It's more massive. So this one has more inertia. It's resisting my push more than this one is. So mass, 10 kilograms versus 2 kilograms, the inertia factor is it's harder for me to get it to not sit there, to get it to move. And it's going to be 5 times as hard to get this one to move. I require 5 times the force to get this one to move as I would to get this one to move at the same rate. So mass is not a measure of the amount of matter. It's a measure of inertia, or how difficult or easy it is to get something to change or to move. That one's a little hard to grasp, and it's just much easier for us to say, oh, it's the amount of matter, and we move on. But it's wrong. And here's another example of why that's not correct. Let's say, for example, that I have lead, okay, a little chemistry here for you, lead and hydrogen. You know hydrogen is much lighter than lead. You know that. Hydrogen is the number 1 on the periodic table. It has a mass, a relative mass of 1. Okay, lead is much heavier on the periodic table. It's way down there and over to the lower, it's over here. So it's heavy. You know that, you know lead's heavy. Let's say that I have 1 lead particle, PB. There's my particle of lead, all right? There's my PB. Now, if you look on the periodic table, you're going to find lead here, and it has a 207 above it. That means its atomic mass is 207 versus hydrogen, which is 1. So if I have 1 lead particle, and its atomic mass is 207, then I'm going to need a lot of hydrogen to equal the same amount of mass as the lead particle is. So I would need, well, you can do the math here. If this has a mass of 207 and each one of these hydrogens has a mass of 1, I'm going to need 207 hydrogen particles to equal the mass of the lead. And I'm not going to draw out 207 circles, okay? I'm not doing it. No, I'm not. But I will put some in here just to prove my point. So I've got a whole bunch of these hydrogen particles, and I need all of these hydrogens to equal the same mass as lead is. Okay, let's go back to that old wrong definition. The definition of mass is the amount of matter something has. Is it? The amount of particles of hydrogen that I have, equal mass to the lead, is a crap ton more. I need 207 of these equal 1 of those. I have a much higher amount of hydrogen particles here than I do lead particles. So in other words, the amount of particles clearly isn't the same, although they would both have the same mass. Mass is not the amount of particles. If I told you that I had a mass of 207 kilograms, it doesn't tell you anything about how many particles I have. I could have 1 particle or I could have 207 particles. Those amounts are clearly not the same. Why that's given as a definition, I don't know. But here's another reason why you know it's not the amount. Okay, so mass is not the amount of matter. You know here as well because in the international system, the agreed upon unit for the amount of matter is the mole. Yeah, you know, don't believe me. I mean, I usually wear a tie. Don't trust me because I usually wear a tie. I'm not wearing one now, but look it up yourself. Mole is the international unit for the amount of matter. The international unit for mass is the kilogram. They're not the same. So how can the amount of matter be equal to mass if mass is in kilograms and moles is in amount, mountains and moles? No, okay. Sorry, that was my little pedestal I was on. And it irritates me that that's still given in some chemistry textbooks as a definition. I don't know. I write them every year. They just ignore me. They pay no attention to this man behind the curtain. Okay, moving on. Here we go. This video is getting long, and I don't want these videos to be too long. And you're all bored out there anyways. You know, you're like, sleeping right now, drool coming out of your mouth. Gross. Okay, I will shortly go through a video on substances, elements, substances, compounds, and solutions, types of matter. I'll make a separate video on that one. Moving on down then, physical and chemical properties. Physical properties are descriptors All right, I can describe this, oh, over here, this is part of my lunch here, this pear, okay? I've got a pear here. The physical property of the pear is kind of a light green, has a pear shape. It's a pear, so it has a pear shape to it. If I said pear shape, you know what that is. That is a physical description. So I don't need to have this undergo any chemical changes to understand what the physical properties of it are. All right, I could actually, I could mask this. That would be a physical property of it. So a physical property is one which shows itself without having to undergo chemical change. Describe it, look at it, mass it, weigh it. Don't do anything to it, don't mess it up in terms of its chemistry. The next one here, that's right next to it, says chemical properties. Okay, chemical properties only show themselves through, after, or during a chemical change. So a chemical property is one that will not rear its head. I didn't say ugly head, it doesn't have to be an ugly head, rear its ugly head. Won't show itself unless the thing is undergoing a chemical change, a chemical transformation. Well, I'll give you an example of that. Okay, iron, Fe, iron. We all know that iron can rust. Iron rusts over time. It oxidizes, it's called oxidation, becomes iron oxide. Iron rusts. So a chemical property of iron is that it can oxidize, that means it's changing, and become rust. Now you've seen rust, you know what it looks like. Okay, it's kind of this brownish stuff that on cars, especially up here in the Rust Belt of the United States, we see rust on vehicles, and we know what rust is. We know it has that kind of that brownish color to it. And, yeah, but iron will oxidize it. Oxidation on metal is a chemical property of that metal. Okay, oxidation is a chemical property of metal as metal undergoes that process of oxidation. A more biological one would be leaves turn color in the fall. They have chlorophyll in them, and there's a chemical change that goes on within the, there's a little bit of biochemistry here, and I've never studied leaves and why they chemically do what they do specifically, but they undergo a change, and we can see that the chlorophyll, so the property of leaves is that the chlorophyll is that they will change to a different color through a chemical process. So chemical changes are seen when a chemical reaction, a chemical change, chemical process happens. Those chemical properties will show themselves through chemical change. All right, let's see. Oh, we're getting up to 20 minutes here. I'm gonna have to stop this pretty soon. Otherwise, they take forever to load these videos. Let's see. Okay, and we'll do one last one here in this video, extensive and intensive properties. Extensive properties are dependent upon amount. So an extensive property is dependent upon the amount of something. So the, let's see, I'll go back to my pear. An extensive property of the pear is it has a mass maybe a half a kilogram. Maybe it's 500 grams. That would be an extensive property of this. So it has to do with amount, how heavy something is, how tall something is, how much volume it takes up. Those are extensive properties depending on amount. Intensive properties do not depend on the amount of something. What are you talking about? It doesn't depend on the amount. Let's take this piece of paper here. Actually, it's kind of a napkin. What color is it? You know, it's kind of tan, brown. What color is it now? Tan, brown. I have less of it than I had to start with, and it doesn't make any difference how much of it I have, it's still tan or brown. So the color of an object is going to be one which is intensive. It doesn't have to do with the amount of the substance, it's just, it is a certain brown color, no matter how much of it I have. But that's a simple one, but the most important one, I won't say, yeah, that's the most important one. I'm going to say it. Yeah, I said it. Important one is the next thing on our list, which is density. Density is an intensive property, actually based upon extensive measurements. Density is mass over volume. Your first lab is going to be a density lab. Okay, that'll be on Wednesday of this week. But density is mass divided by volume. Mass, extensive, depends on a measurement. Volume, extensive, depends on a measurement. But density itself is intensive, although you get density and intensive property by using these two extensive properties. Density is intensive. That means it doesn't matter how much of something you have. It's going to have the same density. Gold. right? We all know about gold. Some sweet stuff, okay? It's good for you. I usually sprinkle it on my toast in the morning, a little bit of gold flakes. So good for you. Gold is very dense. It's one of the most dense substances on the planet. You think lead is dense. People know lead is dense. Lead is like 11.8 density, grams per cubic centimeter. Gold, 19.3. So it's almost twice as dense. Gold is dense stuff. Now, if I have a nugget of gold, or if I have a bar of gold, they're both going to have the same density. They're both 19.3. It doesn't make any difference how much of the gold you have. It's still going to be 19.3 grams per cubic centimeter. That's the density. Density is not dependent upon how much of the material, in this case, my example, gold, that I have. I could have an entire big, huge block of solid gold, or I can have a little sliver of solid gold. And both of those will have that density of 19.3. It's intrinsic property. It's a very important property. It's an identifying property. You can identify an element by just knowing its density. If I told you I have this element and has a density of 1, okay? You know what it is. You know what? I'm not going to tell you. You go look it up. You figure it out yourself because you're all relatively smart people. And I got to stop this video. This is way too long. Okay, here we go. Break.